Hi there, welcome to a short video on covalent compounds. This will be the first of a number of explanatory videos on sometimes difficult concepts. In this particular video we'll be looking specifically at these compounds which exist by having their atoms held together through a sharing of electrons, represented as a bar here in this diagram. What are we going to cover? Well, we're going to cover the nature of covalent compounds. What are they? We're going to look at how they're named, and we're also going to look at how we depict them diagrammatically. How do we draw a molecule of a covalent compound with correct shape and structure and bonding? So by the end of the video, hopefully we'll know a little bit more about these three things. So firstly, what's the nature of covalent compounds? Well, firstly, they exist typically as discrete molecules. So billions of molecules all moving around make up these type of compounds that we see with our naked eye. Examples are water in the case of a liquid, or carbon dioxide in the case of a gas. Alternatively, they may also consist of strongly held together atoms in a more of a lattice type arrangement. We call these giant network solids. An example here is glass. The substances generally are formed from non-metallic elements only. There are exceptions, but generally non-metallic elements are bonded together to form covalent compounds. At room temperature, as I said before, the substances tend to be liquids or gases, but a few solids do exist. Now, the bonding between the atoms within a molecule of this compound, as I said before, are called covalent bonds, and they result from a sharing of electrons in the valence shell, or the outer shell of each atom. In this case, the outer shell of oxygen and the outer shell of two hydrogens, which of course is forming a water molecule, H2O. Typically, the bonding or valence electrons are shared. 2 electrons are shared per bond in this case, and with 1 electron being contributed from each atom within the molecule. So you can see here 1 electron shared from the hydrogens, and 1 electron here shared with this hydrogen from the oxygen, and another electron from the oxygen shared with this hydrogen here. These 2 electrons here form the bond. So we say a pair of electrons forms a single bond. Now, and this can occur up to a maximum of 3 bonds, or what we call a triple bond. So a sharing of 2 electrons is a single bond, 4 electrons a double bond, and 6 electrons a triple bond. Now, electrons tend to be shared in such a way so that the outermost shell, or valence shell, contains 8 electrons typically. This seems to be a stable arrangement for the electrons. There are exceptions, of course, like hydrogen can't have 8 in its outer shell. It has a maximum of 2, so once it gets those 2 in its outer shell, it forms a stable arrangement. Well, let's move on. As stated before, there are different types of covalent compound. 2 different types, in fact. One type exists as discrete molecules, the other as a lattice. The discrete molecular type covalent compounds, they tend to be liquids and gases at room temperature, and of course, because the molecules are free to move around, this gives these type of compounds a fluidic, or a fluid type nature. That is, they can be poured, they can disperse, they can diffuse as the molecules spread out. Examples include water, ammonia, it's a gas, hydrogen chloride, another gas, and nitrous oxide. Common name for it, its UPAC name is dinitrogen monoxide. Of course, the other type of covalent compound is the giant molecular lattice, or giant network solid, and they typically have high melting points. They consist of a very strong three-dimensional network or lattice structure. Examples include glass, where you have silicon and oxygen bonded together, or carborundum, which is an abrasive, and its formula is SiC, or silicon carbide. So there you go. Different types of covalent compound. They can exist as solid, liquids, or gases, but generally solids and it's generally liquids and gases at room temperature. Now, how do we name them? Well, there's a couple of examples here. We've got nitrogen dioxide here, and we've got dichlorine heptoxide. You can see that the nitrogen dioxide has a couple of bonds here, and we can see double and single bonds within one molecule of dichlorine heptoxide. So I'm sort of hinting at how they're named. We do have to name both the type and number of atoms within a molecule in order to actually give the name of the compound. Now, the number of atoms is given by a Latin prefix, and here is the table. So, for example, NO2, it's called nitrogen dioxide di because there's two oxygens. This molecule here, as I stated before, there's two chlorines, dichlorine heptoxide, and we also have sulfur hexafluoride. Now, you might ask, well, why is the nitrogen first, or the chlorine first, or the sulfur? Why isn't it F6S, for example? Well, this has to do with the electronegativity of the atoms. Nitrogen and sulfur tend to be, and overall chlorine in this molecule tend to be less electronegative than oxygen or fluorine, and they tend to be at the center of each molecule. But we're going to talk a little bit more about electronegativity and polarity in another video, so we'll leave that one for the moment. How are the compounds depicted diagrammatically? That is, how are we supposed to draw them or allow people to understand what we know about covalent compounds? Well, there's a number of ways covalent compounds are drawn. We typically draw a single molecule of the compound, but we understand that within a sample of the compound you will have billions of these molecules. We can draw them as concentric circles. This is useful if we want to show how the bonds are made up by an electron being contributed from each atom within the molecule. Alternatively, we can draw it as what we call an electron dot diagram, where the valence shell electrons are drawn as dots, and we typically pair them up like so, although we're reminded that the electrons don't exist in space as pairs. Alternatively, we can replace the bonding pairs of electrons here and here with lines, and a single line here represents a single bond, and we keep these unbonded pairs of electrons, which are called lone pairs, here and here, and they tend to orient themselves as far apart from each other as possible, given that they're negatively charged. This sort of diagram, where we show lines as bonds and lone pairs of electrons, are called Lewis structures or Lewis diagrams. So what we want to talk about now is how we actually go on and draw a Lewis structure for a particular compound. Now, there are a few rules, and of course, as always in chemistry, there's a few exceptions to the rules. So what we're going to pick on at the moment, compound we're going to pick on at the moment is sulfur dioxide. I could choose any simple covalent compound, but I'm going to choose sulfur dioxide. Note that it's a molecule consisting of one sulfur and two oxygen atoms. But how are these actually bonded together. Sulfur, being less electronegative than oxygen, appears at the beginning of the formula and also is the central atom in the molecule. Now, I'll just step us through a process in order to draw it. So the first thing we need to remember is to determine the number of valence electrons in each of the atoms within the molecule. So there's one sulfur and there's two oxygen atoms, and both oxygen and sulfur are in group 6 of the periodic table, which means they all have 6 electrons in their outer shell. So adding up all these electrons gives a total of 18 electrons. Now, there is a drive towards octet. So what we're saying is that oxygen, sulfur, each oxygen in the molecule and sulfur will try to get 2 electrons or share 2 electrons in order to get 8 in their outer shell. Now, if there's 8 in the outer shell of each of the 3 atoms, well then this is the actual total number of electrons needed in each atom in order to form octet. So that's the step 2. We need to actually work out the total number of electrons within the molecule if each atom in the molecule was to achieve octet. In this case there's 3 atoms in the molecule, so 3 times 8 is 24 electrons, potentially 24 electrons there in order to achieve octet for each of the atoms within the element. Now, in order to determine the number of bonding electrons, so that we can actually work out the number and type of bond within the molecule, we have to subtract the valence electrons from the total number of electrons. So doing this gives us a total number of bonding electrons, in this case 6. 24 minus 18 is 6. But we have to remember that for a single bond requires 2 electrons, a pair of electrons. So in order to work out the number of bonds within the molecule, we need to divide 6 by 2. This will give 3 bonds. So what we can say then is that within a molecule of sulfur dioxide there are 3 bonds. So how do you distribute 3 bonds between 3 atoms? Well, there's really only one way, and there it is right there. You have 2 bonds between one oxygen and a sulfur, and you have 1 bond between the other oxygen and the sulfur, with the sulfur taking the central part of the molecule. So we find then that this is what can happen. We have in the oxygen a double bond here and a single bond here, and once we actually draw in the bonds, then we just simply put in any existing lone pairs that make up 8 electrons around each atom. In the case of, let me explain, in the case of sulfur, these 2 bonds here represent a sharing of 4 electrons. So that's 4 around the sulfur already, and another 2 is 6. So therefore we need to put in a lone pair of electrons to make sure there's 8 electrons around the sulfur atom here. In the case of the oxygen here, well, this is a sharing of 4 electrons, so 4, and we add another 4 electrons to make 8 electrons around the oxygen here. And in the case of a single bond here, well, that's 2 electrons shared, so we need 3 lone pairs in order to achieve octet for the oxygen. And this is the structure of sulfur dioxide. Now, down here you can see that the sulfur dioxide is depicted as a linear molecule, but that's not entirely correct. What happens is that the lone pair on the central atom of the molecule tends to repel the other electrons away from itself. So we get this sort of structural arrangement. It's called a bent molecule or an angular molecule, and that's what sulfur dioxide looks like. Now, the positive and the negative part just refers to the fact that overall there tends to be more electrons around this oxygen here, giving it an overall negative charge in space on this side of the molecule, whereas there's fewer lone pairs on the sulfur, giving it a relatively positive charge. Even though the molecule itself is neutral, in free space, one side of the molecule tends to contain a more dense arrangement of electrons. We say in this case the molecule has polarity in space. But again, we'll talk about that a little bit more in another video. Now, another thing that we need to note is that sometimes, which one is correct here? We can draw sulfur dioxide this way, or we can draw it this way. And it's not simply flipping the molecule over to form this. What scientists have found is that when they measure bond length using infrared spectroscopy, is that the bond length, and there are standard bond lengths for double bonds and single bonds, but the bond length of sulfur dioxide appears to somewhere between a double bond and a single bond. So what scientists think is that there's a rapid switching between these two states. What happens is that this single bond here comes down, and this lone pair here, this lone pair comes down and forms a double bond, and this pair of electrons here moves up and forms another lone pair here. So you can see it happening here. And so we find that sulfur dioxide, well, scientists believe sulfur dioxide actually oscillates very quickly between these two extremes. Now, molecules that exhibit this sort of behavior are called resonant structures. We say that sulfur dioxide exhibits resonance. Now, resonant structures tend to be more stable than non-resonant structures. There is one other thing that can happen in sulfur dioxide, and this is in further studies of sulfur dioxide. In some situations, sulfur dioxide can form two double bonds with oxygen here and here. So if you were to draw sulfur dioxide like this, that would be fine, but from our process that we spoke about previously, it's preferential to draw sulfur dioxide like this. The reason being is that in this case, while the octet rule is obeyed with oxygen, it's not obeyed in sulfur here. But that's okay. Sulfur can have what we call an expanded octet because it can fill up D sublevels. Now, sulfur in this case has 4, 8, 10 electrons around it. Not in the valence shell. It'll have 8 in the valence shell and 2 in the D sublevel. This is possible, and so we find that various structures exist for sulfur dioxide. One further thing, if you look at this particular arrangement here, and that's quite a correct way to represent sulfur dioxide, we find that, okay, we've got 2, 4, 6 electrons around oxygen, which is what we would expect given that it's in group 6. But if this oxygen here was to form a single bond with the sulfur, it would mean that there would be 1 extra electron being contributed from the oxygen, giving a total of 7 electrons around the oxygen. Now, is this true? Well, no, it's not really true. Oxygen has 6 electrons in its valence shell. We've got 6 electrons here, so where does this single bond... You see what I'm saying? The oxygen has no electrons to contribute to the single bond if there's 6 electrons here. So what's actually happening is that the sulfur is actually contributing both electrons to the bond. You see, sulfur also has 6 electrons around itself. There's 2 here. See the 6 electrons here? There's 2 here. There's 2 being contributed to this double bond here. That makes a total of 4. We find that the other 2, which are here, are being contributed directly to the bond. Now, in cases where an atom within the molecule contributes both electrons to the single bond, so that you're not getting a sharing of 1 electron from each atom, that's okay. You can have 1 atom in the molecule contributing both electrons to a single bond. If this happens, it's called a dative covalent bond. Some textbooks refer to it also as a coordinate covalent bond, where both electrons are contributed by one atom to form the bond. There's a little bit of a rundown on how to draw Lewis diagrams. If we stick to the process, we can't go wrong. There are of course exceptions to every rule in chemistry, but at this level we won't be giving you too hard a problem. I've given you some examples here to the octet rule. For example, beryllium's in group 2 on the periodic table. It's got 2 electrons in the outer shell. So if it was contributing 1 electron to the bonds, and here it's bonding with chlorine to form beryllium dichloride, well, chlorine's fine. It's contributing 1 electron to the bond, so chlorine gets 8 in its outer shell. It's happy. It's forming the octet structure. But you can see here that beryllium only has 4 electrons in its outer shell. Certainly not octet, but still a stable arrangement. It is reactive. It will gladly accept pairs of electrons from other compounds in order to react to fulfill its octet structure. Similarly here, boron trichloride. Boron's in group 3 on the periodic table, so again octet is achieved with chlorine contributing 1 electron to the bond, but you can see that there are only 6 electrons in the outer shell of boron. And again, as before, boron will quite happily, the central boron atom will quite happily react with other compounds in order to get 2 more electrons to achieve octet. Sulfur, is like in the previous example here where you have an expanded octet for sulfur. Well, again, there's an even greater expansion of octet here in this sulfur molecule. This central sulfur atom here, this is sulfur hexafluoride. So we can see there's a central sulfur atom surrounded by 6 fluorine atoms. Well, again, fluorine's in group 7, so it can quite readily contribute 1 electron to the bond, and it's doing that quite well here. We find that so each fluorine can quite happily form a single bond here, and each fluorine has achieved octet, so 2, 4, 6, 8 electrons. But we can see in order to do that, sulfur has 2, 4, 6, 8, 10, 12 electrons around itself, 8 in its valence shell and 4 in the D sublevels. So there you go. There's the nature of covalent compounds, how we name them, and how we draw their structures, plus a few examples of exceptions to the rule. Thank you very much.